Can you hear me?
Yep.
Okay. I think I'm getting some feedback, but all right. Right. So as Allison said, please, I really hope that this first session will be interactive and mostly in getting feedback from everybody. It's going to be a very, let me find my mouse, a very kind of simplistic introduction to deep learning. It's really meant to get everyone kind of caught up with the very, very big picture ideas. I've talked to some of you, and I know there's been some polls around and stuff, and I think there's a people are coming at it from very, very different directions. So I think just kind of getting everyone kind of on the same page with the main concepts will be the goal here. So I kept thinking about what teasers to add at the very beginning, and I probably don't need teasers. I think everybody has, is excited about deep learning one way or another, or scared of it or something. But I thought, okay, well, other courses show fancy images, so maybe we could show fancy images. This is a reconstruction example where, with the help of deep learning, you can get much sharper image reconstruction that you see on the right than you might with classical methods. But I think more representative kind of idea of what deep learning is nowadays is this paper, which I just took the screenshot from Google Scholar, and I think everything about it is representative of deep learning. So it's a really fancy title. It says radiologist level pneumonia detection from chest X-rays using deep learning. So it's a bold claim, which I think is par for the course with deep learning. It's really applying a large and fancy deep learning model to a real clinical problem, using X-rays to detect pneumonia. It has 500 citations per year in the last 3 years, so it shows the excitement. It's also only on arXiv, so it hasn't been published or peer-reviewed, and yet it's incredible. It has incredible amount of interest, and I think this Pranav, who's the first author, is going to be a professor here at Harvard, and I think he does really good work. But I think overall this paper kind of shows both the incredible excitement and the type of claims that come out of deep learning nowadays, but also kind of how the model has changed. Not necessarily having to wait to have a paper published before it has a big impact. And what I really think, kind of says that deep learning is here to stay is that industry has really kind of taken over now. This doesn't have a y-axis, so it's a very scientific graph, but it's the amount of investment and revenue that companies are sort of seeing explicitly related to deep learning. So it started 5 years ago with 100 million, and now we're in the billions. And that just to me tells me that this is real and it's going to be here to stay, not just not just a research gimmick. But what's interesting is because of that excitement, the industry is developing a lot of open source platforms for everybody to use for deep learning. TensorFlow, PyTorch, JAX. We're going to talk about all of this at some point, but the main sort of takeaway is that there's so much interest in both research and industry that there are these entire frameworks and infrastructures that are being developed, all of them free, for some definition of free, and supported by really large industries. And that's sort of, to me, the main signal that this is something we're gonna sort of be looking at for a long time. All right, so what is deep learning and sort of what is this course about? So I'm calling it a mini course, I guess, or summer school or something. I know there's a lot of interest in the lab. I've been developing on the side, preparing a course for HST. And so we thought this is a good opportunity to kind of test out some of the ideas in the course. And the idea was today, there's going to be a little bit of this logistics conversation about, what are people interested in. where I'm going to do a very, very, very basic introduction to what deep learning is. So, as I have here at the bottom, if you're already doing research in deep learning, as some of you are, you're going to be really bored today. But I think it's a great sort of opportunity for everyone else to ask questions and get up to speed. And then in future sessions, we're going to take deeper dives on different aspects of deep learning and with a focus on neuroimaging applications. So we'll have the usual kind of segmentation, registration, reconstruction, things that you will have seen or heard of that I think will be of interest to people in the lab. And there's many aspects to deep learning in terms of fundamental sort of methods and also how to use it. And so we're going to try to do our best to cover these in a few lessons. I'm sure it's not going to be enough, but we have an education channel on Teams to help with all of this. So I wrote here that no background is needed for today, which means that if I say something that you don't understand, please just interrupt, because I did promise there's no background needed. All right. So who's this course for? So, we're doing this for LCN and friends of LCN. So I will have an HSC sort of full-fledged course at some point. But, I'd like to take a second for people to kind of tell me what they hope to get out of it, because there's quite a few people in the audience. And I'm sure different people want different things out of it, or you're kind of hoping to learn something. So I'm wondering if people could really unmute and tell me what they think they should get out of this, and we'll try to adapt based on this. Anyone want to unmute? Am I talking by myself? Am I not connected? Is that...
We can hear you.
You can.
Okay. Any?
I can go. I have a
Yes.
maybe an unusual question or perspective on this. As someone who's very interested in clinical translation, one of the disadvantages of deep learning, in my opinion, is it's harder to make claims about the model. So at Cortical Metrics, for example, we developed a normative model. We got that FDA cleared, and we argued that so the FDA wanted to know that how did we know all the inputs to the normative model were accurate, right? Or not, were not adversely affecting the parameters of the model. So what we managed to argue was, okay, well, we can, for every data point, we can compute, the leverage or the influence of that observation on the model parameters. And then we could say that since the vast majority of the data points have a negligible effect on model parameters, we don't have to QA them. So I guess I've always had in the back of my mind, how could I construct a similar argument for deep learning algorithms?
Yeah, I think that's a great question. I think it's going to be in one of the more advanced lessons. But I think we're going to talk about things related to that, and in particular, how data affects the model, and then how the model can generalize. And I think it's a focus for a lot of research as well. I think we've made great strides, to be honest with you, compared to, say, 3 years ago, in terms of our ability to explain what's happening with the models and also understand how generalizable they are, so how they will affect different types of data to process different ways. Okay, but that's good. Thanks. Anybody else? I really, wish people who maybe have very limited experience could unmute and say what they hope to learn. Because the more questions I get now, the more I know how to adapt the course. Nobody? Really? This is going to go fast if nobody has any input.
Can I make a comment? I think my point is also related to what Paul was saying. I would love to have a discussion on validation, especially with medical problems of just deep learning methods.
Okay.
Like, how do you validate when it's a black box, basically?
Sure. Okay. Yeah.
I have one point.
Mhm.
Recently, I've seen a lot of people trying to train a model to for different modalities, especially in optical imaging. For example, from low resolution to high resolution. Wonder if you can talk about that. For example, you want to train a model to link MRR data to optical data. Is that
Right?
does that make sense?
Yeah. Well, we can. Yeah, I mean that's a good suggestion. We could definitely do that. I'm trying to think. Okay, so I'll keep that in mind. It's probably you know, we should have we'll probably have one sort of lesson that's focused on things related to synthesis and reconstruction and that sort of thing. And it sounds a little bit like it will fit in there. What your question is. I certainly won't cover anything about that today. It's much more basic today, but I will keep that in mind.
Okay. Yeah. All right. Thanks.
My comment is much more basic, and I'm sure that you're already covering it. But I would want to know, like, how do I start? Like, if I have a problem, like, how do I start? How do I choose, like, the base architecture? How do I choose or tune the parameters? And, like, yeah, how do I make, like, the decisions? Like, do I do batch normalization or not? I don't know. Things like that.
Yeah. Okay. So that's great too. So I think what will happen is because today we'll just do a basic intro and then Andrew will do a bunch of Python stuff. I was thinking next session will be actually focused on all these, like the various aspects of choosing the model and the tricks to make it work. It's certainly more than I can cover in 1 hour, what your question is, but I think I'll cover the usual ones. So thanks. Yeah, that's a great question. Yeah. Anything else?
I'm with Aina. It's like, how do I start? How much data do I need to provide? Like,
yeah, that's a good. Okay. How much data do you need to provide is a great question for every task. Can you tell me a little bit about the tasks you're thinking about?
Segmentation, right? I mean, that's the first one that comes to mind right away. But if I were to want to do some segmentation of neuron on OCM images, I have a bunch that are already segmented, but how much is enough for you for models or not?
Right.
That's this, but that can be also just OCM, different layers, segmentation of layers based on how many data do you need to like start being relevant. Useful. It's a lot,
no, those are great questions. Yeah.
It's a lot of manual segmentation. And are we talking like full slice segmentation, or is one neuron a data point? Like, you know what I mean? It's like, what exactly is the data for you?
Yes. It's a great question. The sort of short answer is that it depends on the problem, but I think you have a concrete problem, so it's a great question. Not a lot of data, but I think that's you're right. It goes with Aina's question in that it's sort of about decision making for the task. So unfortunately, I'm not going to have these answers today. I actually have a slide at the very end that says I'm going to cover these things next time, and I think it's exactly what the two of you have asked. But I will definitely keep those in mind. Is there another question? I think some.
Hamid? Yeah, I also had one question. So thanks, Adrian, for taking the time to present this.
Yeah.
I have no experience with deep learning. So my question is, as I understand, like from the tasks that you were discussing, segmentation, registration, image reconstruction, etc. So as I understand, always the input to your models are like the images, like 2D or in some sort.
Right, in these examples, yeah. Mm-hmm.
Exactly. So my thinking is that, is there also, would you also discuss about alternative ways rather than, I mean, if you have, I'm working with like deriving models, so taking like an MRI scan and transforming that into like a graph model or in whatever type. And basically from that model, you can extract like a huge number of features. So basically you represent the image in a different format. And I'm thinking, can that format be inputted? Will you be discussing anything in that regards, or will you be just image focused?
No, yeah, I can. I certainly can. If there's interest, I mean, this is part of why it's great that you're asking the question. I think if there's interest, we can discuss it. Certainly the concepts I'll talk about today are very
focused on. I'm very much focused on the model part, so I'm interested in this. If I can see, I can also use the model, not just put it away and just switch to like deep learning, but can somehow link it to like the outputs that I can get and just learn through that.
Yeah, absolutely. Okay. Definitely. Yeah.
Thanks.
Anything else, or should I know, Lila, you on?
Oh, I just have a very quick one, and it's probably a very general question. It's like, how do you stay on top of all, right? Like just your simple example from the 2017 paper, with the yearly 500 citations, I mean, obviously you can keep following literature in your own field, but there's just so much that comes out, right? Like things are not even published, as you mentioned. They are on arXiv, they are on whatever, GitHub. And, probably you cannot answer for the field, but, whether you have favorite, I don't know, you probably have favorite conferences, favorite groups, or, how do you filter through all of this?
Yeah, I mean, that's a great question. To be honest, I didn't think about covering that, but I think that should probably just be a discussion at some point, maybe at the end of one of the sessions, how we all do it. I certainly don't have the magical answer, to be honest. I have my own heuristics, but there's a lot of people here who have to do the same. So it's a good point.
So one last thing, I know I had heard from a lot of research assistants that what they wanted to learn was just sort of the basics of what they need to know for this. That it is the hot new thing, going to grad school, and what should they know about this before they go to grad school, basically.
Yeah. That's a great question. So what I'm going to try to do today is give you some very, very basic fundamental, kind of the difference between what dominated machine learning before and what deep learning is very fundamental. I will give also, there's a nice demo set up by people at Google that I think we can go through together. And I think it'll give just like the intuition of how it all works. And I think then the rest of it ties in with the questions earlier about, how do I think about sort of decisions around a model and such, which I think will give an intuition about how all this works. If I don't address anything that's been asked, please kind of let me know later on in a session or two. Okay, so I do want to mention there's an enormous amount of other resources, especially now with COVID. A lot of people are putting their stuff online, which is great in some ways. It's also, there's a lot of stuff that you go on YouTube and you search, deep learning introduction, and there's a lot of videos that are there that are not very good, and they'll kind of take you down the wrong path. So I would suggest, Leah sent this email about, if you have resources, send them to her. Maybe we could collate something together, and I'm happy to kind of go through them and say which ones I think are of good quality. And I'm sure other people here will do the same. But so MIT has what used to be a brief course, but now it's a little broader. It's very general, so it will cover deep learning in self-driving cars and that sort of thing. But it is a very good quality, I would say, kind of survey. So it doesn't go in really deep math, but it does cover a lot of different types of deep learning. Neuromatch Academy is another free one that's really good, and it takes a very different angle. It's very neuro-focused, which I think a lot of people here will like. It's got a focus on sort of creating groups when it actually sort of runs, and if you actually sign up to this course. But it also has the kind of YouTube and tutorials online. There's a lot of discussion about what the connections are between deep learning and how the brain works, which I think is more philosophy than anything, but it's really interesting. And then I think if you really want to kind of go from not knowing necessarily too much about it to really being able to code models, I think Coursera and edX courses are where you should go. And I'm happy to give specific suggestions depending on any one person's level. But these are kind of like my recommendations if you want to take on more lessons maybe after this course is over or in parallel or something like that. I really don't recommend going on YouTube and typing sort of introduction to deep learning. And so in this course, we'll focus on some more neuroimaging examples than anything else. And I'm hoping that the sessions will be interactive, questions and tutorials and such. All right, so today I'm just gonna go do a brief intro to deep learning, and then Andrew Hoops will give an introduction to sort of Python and a bunch of tools he's created. I don't know what the name of the library ended up being, so I'm very curious, Andrew. I'm gonna have to leave partway through part 2, unfortunately. But I think everyone knows where to find me or where to find Allison. All right, so just to make sure, I'm going to mention machine learning and deep learning. This is kind of how I think a lot of people accept the terminology to be AI, is this general, nebulous, vague term that kind of includes everything, from hype to actual research. Machine learning is basically, it kind of encompasses anything where we have models to learn from data. And when I say learn, I mean they sort of adapt to a particular data or data set. And deep learning or neural networks are a particular type of machine learning. Okay, so and when I talk about machine learning, I'll really be talking about 2 types of problems that I think basically everything we do kind of can be part of, which are classification and classification and regression. So classification means you have a bunch of data that belongs to a bunch of different classes, and you'd like to have a machine that tells you what every data point, what class it belongs to. And I think regression probably. Yeah.
Sorry, Adrian, I just wanted to point out that on your previous slide, like I agree with that division of the nomenclature, but many people these days, when they say artificial intelligence, they mean deep learning. Like when you talk to a clinician, they say an AI, they mean a deep network. And that's really common these days.
Okay. I would say when a clinician says AI, they might also mean linear regression. So it's a little hard to tell. Which I guess is a form of deep learning, just very shallow. Okay. So these, I'll be talking a lot about these sort of problems, classification and regression. It's just, you'll see these sort of graphs up, and I just want everyone to sort of get the idea. But okay, so machine learning in general is about having a function. I'm going to simplify things a little bit just for ease of description. But the idea is to have a function that takes you from one type of data to another. So in our world, you might mean you want to go from an MRI to a desired output, like diagnosis. And it would be great if we have a function that has a bunch of knobs or parameters, and we can fit those parameters to data, right? So maybe you want to do this on a particular type of MRI, and you want the machine to learn this relationship between MRI and diagnosis by essentially adapting parameters. And the problem, classically, when I mean classically, I mean the machine learning we used to work with until 3 years ago, was really that we didn't have all of the pieces in place to have really large models to do the job. So what we tended to do is that we would break this function up into a bunch of manual design. So we would come up with our own sort of very specific model to a very specific task, and then a little bit of learning. So most of the work went into designing the model, and the learning was really not sort of the big focus, I would say. So we did things like, figuring out how to extract features from the data. So for example, if you wanted to take an MRI and predict whether someone has Alzheimer's disease or not, let's say, you might extract features that you might think are relevant to Alzheimer's. So you might, look at the atrophy of the brain. You might look at the hippocampal volume, things like that. And so these would, to a large extent, be manually designed. We would think about how do we measure atrophy? How do we measure the hippocampus automatically? Things like that. And then oftentimes we would have a fairly constrained, what I would call simple model, though I'm sure people will argue that definition, but simple by today's terms, learning aspect. So you might do, for example, you might extract all those features, and then you might just run a linear regression or a logistic regression between those features and the Alzheimer's diagnosis. And in running that regression, you had to learn a few parameters that kind of said, well, how much do I weigh the hippocampal volume? How much do I weigh some other volume or atrophy or something like that? And a lot of machine learning had this form where basically it was an awful lot of human effort in designing the algorithms and the features very particular to a type of task. And that was a good thing because it led to some successes, but it was difficult to design all of these aspects, right? You needed domain knowledge, you needed a lot of effort, a student doing their entire PhD on a problem, that sort of thing. So, it's a hard thing to do. And the designs were very limiting. For example, if you thought atrophy was useful to diagnosing Alzheimer's, but that's the only feature you extracted, you might miss other important aspects of the brain that could help you, diagnose Alzheimer's. So in some ways, the fact that we designed models was a great thing, but it was also a limiting thing. So that was kind of, I would say, though I'm sure I would get a lot of pushback, but that was a popular paradigm for designing machine learning models. And the learning aspect, where you learned a few parameters, that tended to be very limited. It wasn't a lot of parameters that we would learn, and they weren't very, they didn't have a lot of degrees of freedom. Is there any question about that paradigm in general? Does that make sense? Any questions? No? Okay. Either it's very clear or nobody understands, but move on. And so the contrast here, I'm abstracting some of that specifically to go into deep learning quickly. So the contrast with deep learning is that in deep learning, we're trying to kind of do the opposite. We're trying to have very, very, very rich, large, powerful models, but those models are built from very simple building blocks, very simple steps that are not necessarily designed to a very particular task. They're just general building blocks that are powerful in many ways when put together. So let me kind of show what this looks like. So instead of coming up with a very sophisticated, very specific model for Alzheimer's prediction, you would first take a brain image or whatever your input is, and you would push that, you would sort of have these very simplistic operations on this image. Okay, and so one of these simplistic operations is one of these building blocks, right? And so a simplistic operation might be a multiplication or an addition or something like this, right? So you multiply the brain image by some number, or you add to it or something like that. So it's a very simple operation. It wouldn't do you any good if you just had a couple of these, but because it's simple, you could have a ton of these operations and you could stack them. So you take the image, you do maybe 100 or 200 of these operations, and then in sort of the next step, you do 200 more, where the output of each of the first operations goes into the sort of second step. Okay, now each of these operations is or each of these building blocks is very, very simple. It's not sort of designed specifically to do Alzheimer's, but the idea is that by stacking these wide and deep, we're going to be able to create approximations to very complicated functions that we're after. Okay. So this is kind of where the definition of deep learning comes from, in the sense that we're stacking a bunch of these operations, and sort of the going from left to right is what people refer to as the depth of this neural network. So that's really the basic idea of how neural networks work and how deep learning works. It's really not complicated at an abstract level. The complicated parts come into how we are able to learn the parameters or fit the parameters of each of these operations to, operations to kind of make this network do something useful. And deciding on what people asked about earlier, how deep and how wide and what are these actual operations. But the main idea is just this kind of stack very small building blocks to make it, to sort of have a large, powerful model. So I do want to take a second here to ask people what, does this make sense? What are the questions? And especially for people who kind of haven't seen necessarily deep learning before, does this whole thing make sense? I am going to wait for people to unmute. I'm sure there's some people who would like to unmute and say something, maybe. No?
I have questions.
Yeah.
So for the simple operations, these building blocks, are there criteria for what allows something to be included as a simple operation, or is there like criteria that means something is too complicated to be used as a building block?
So you can do anything in these operations. You could make, sorry, I shouldn't say anything, but you can do a lot of things in these operations. They don't actually have to be simple. The advantage of having them be simple is that they're really easy to work with and stack them and learn their parameters. The real constraint is something I haven't talked about, I'll talk about next time, but basically in order to learn the parameters, we have to differentiate through these, sort of be able to take to mathematical derivatives. And that's really the main constraint. Each of these operations has to be differentiable. But we'll talk about that later. But I think conceptually, almost any operation you think of can be made to be differentiable. So I would say in practice, there aren't strong limitations on them. But the main idea is that we stack very simple things because that makes our life easier. Bruce has something to say.
Well, I was just going to give an example. Like by far the two dominant things that are done are matrix multiplication and convolution, each with some type of nonlinear function at the end of it, a sigmoid. That like those two account for, I don't know, certainly more than 90% of deep learning, if not more than that.
Yeah.
Okay. And do we have like a lab specific example just so I can wrap my head around it? So let's say it's matrix multiplication. Are you saying like rotation or some type of registration?
No, it's really just multiplication. Like think about taking the image and multiplying it by some number, and that number will be learned by the network. But that's it. That's the multiplication operation. Does that make sense?
Makes sense about the operation, but why would we do that to an image? Like, what's the end goal?
So if you stack a bunch of these operations together, so I'm going to actually have some demos that kind of show why this works. But if you stack a bunch of these operations together, simplistic operations together, over time, you're building more and more sophisticated functions that operate on this image, right? Does that make sense? So eventually the function in this slide is go from an image to Alzheimer's or not, right? And that's a very complicated function to try to design ourselves. And so these building blocks, when stacked together, are able to build more and more complex functions. Does that make sense? Sort of.
So convolutions might be an easier example, Leah. Like we frequently think of a convolution kernel as looking like the thing that we want to find in the image, right? If you want to find a diagonal line, then you have a convolution kernel that looks like a diagonal line, and you run it over the image, and where it gives you a big output is where the image looks like a diagonal line. Right? And so in the deep learning context, instead of specifying what the kernel looks like a priori, you learn the kernel. And then you learn not just the one kernel that maybe finds diagonal lines, but then the next kernel would learn how to process filters from the previous kernel. Right? So you run the diagonal line finder over the image, you get a bunch of diagonal lines, maybe you get a bunch of vertical lines, and then you have the next filter, which presumably knows what to do with vertical and horizontal lines or vertical and diagonal lines in order to find the hippocampus. So it's kind of this array, hierarchical stacking of features that, in theory, give it the representative power.
Is that okay? There's the thumbs up. So what I'd actually like to do, because I think it's a good time for these, is to do a little bit of a demo. So I'm going to stop sharing for a second and switch screens. And this demo is very basic, and it's thanks to some people at Google. But I think it really maybe helps with Leah's question and also give an intuition what's going on. So, okay, does everyone see this little, I don't know, window? Or could someone say if they do?
Yep.
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 All right, so what we're doing here is, so we have some data, and we're trying to classify it. So the data have 2 dimensions, X and Y, okay? And here's a bunch of orange dots, and here's a bunch of blue dots, right? And this is a very simple classification problem. What we would like to do is we would like to learn a model that separates the orange dots from the blue dots. And so all in this case, all it can do, all that the model can do is it can learn to draw a line in this space that separates these two. Okay. Is there any questions about the setup? Because I'm going to show more and more complicated examples here. Yeah, it's simple. So you get these 2 dimensions, and you get to have one operation, one line that you get to draw. And so right now, this line is initialized to kind of separate these 2 classes. Just by chance, it happens to be initialized this way, but it's actually initialized wrong. It's saying everything to this side is blue. You can see that by the background here. And it's saying everything on this side is orange. And so it's classifying everything incorrectly. This is just by chance. But what happens when I click play is the parameters of this line are going to start trying to adapt to separate these classes. Okay, and so I'm going to click play, and very quickly you can see that it found this line, and everything to the right should be blue, everything to the left should be orange, and it did this right very quickly. This is with a single one of these little operations, and it's an operation that basically separates this space in 2. Is that example clear? Because I want to show, and I think this relates to Leah's question of why would you want to stack these sort of simple operations? Yeah. Okay. So so this was a simple problem, but what if we have data that looks like this, right? What we would like to do is we would like to have a model that can accurately classify these dots as blue and these dots as orange, right? But of course, if all I can do is draw one line, I'm not going to be able to do that. So when I click play, it's going to try its best to draw a line, but it's not going to be able to do anything useful. And so what what we can do instead is we can say, well, what if we add a few different a few different operations that are very simple kind of lines, and then we stack a few what we call layers of these lines, right? So just like in my drawing earlier, we now have a few simple operations, and then we have a few different stacked lines. And now we're going to try, I'm gonna make a small change here. So now we're going to try to fit this model. And so what this model is now trying to do is each of these is trying to learn its parameters such that the output best simulates this space. And so you can see that now, I'm going to pause it for a second. You can see that now what these layers have achieved is they've sort of managed to say, oh, this area here is probably all blue. This area here is probably all orange. But it's done this by just operating on these very simple sort of multiplication and addition operations. Now, each of these little operations only draws a line. So for example, this one drew the line that way. This one drew the line that way. This one drew the line that way, right? So it's just a bunch of different lines. But then when these lines are combined, we're starting to get more interesting shapes. And then when these shapes are combined, we're starting to get even more interesting shapes. And so each of these operations does a very simple, mathematical multiplication or addition of the previous lines, but stacking lines together, you get more and more complicated shapes. And then in the end, you're able to carve out this space. Okay, so does that kind of make sense? Do people, is that, I don't know, any questions there? Leah, does that kind of make sense about how stacking simple operations can help you?
I think so. I think I thought the operations before were literally additions or multiplications to like voxels in the image. But I think this example you're saying the operation is addition or multiplication between the layers.
So they're addition or multiplication of whatever came before. So for this operation, it's it's addition multiplication of the actual input, like the voxels, if it was an image. But you do a bunch of this, and then in the next layer, you're going to do additional multiplication of the output of these operations, right? So, and additional multiplication is, it's just one operation. Like Bruce said, you could do something simple like convolutions, or you might do some nonlinearity like adding a sigmoid, but they're all very simple operations. And so they're all operations on whatever came before. So the very first layer does operation on the images, and then the next layer does operation on whatever came out from here, and so on. Does that sort of make sense?
Yeah. Okay.
How would you troubleshoot operations like, for example, if you wanted to get a better output, like how would you know if you wanted to fix like the stack of operations, let's say in the second column or the third operation? Like, is this just kind of trial and error, or?
It's a good question. I think there's both a level of trial and error and an intuition that you build over time. But as a concrete thing that you could do, so what this interface, for example, allows you to do, and you can do this in your own code, is you can look at what the output is of each operation that's been learned. So for example, here, you can see how this operation has tried to kind of separate the space. And you can see that what it's trying to do here is it's trying to draw that inner circle a little bit. So this helps you at least get an intuition of what that operation is able to do. And so we call this looking at the features. So that's, one kind of debugging strategy. But to a large extent, I think after working with this, or talking to people who have worked with this, you'll have built an intuition about what works, what doesn't, and kind of like what are the sort of effects that each of these operations have. It's a great question. I think everyone asks, how do we debug neural networks? And like, I think Divya said, it's a black box to some degree, but that's kind of how we do it.
Yeah, the other thing I would add, Ren, is that when you're training it, you're not learning each feature in isolation. Like the training is training everything at the same time. It's not the case that you add one line and then think, oh, how can I add another line? But you're kind of back propagating the errors through the entire network and updating everything.
So it's like a holistic approach, I suppose. Like,
right.
Yeah.
Yeah. Yeah. So you're learning everything together, and I think a lot of people have. I'm not going to touch on this course, so maybe I should. But a lot of people have kind of argued that this is similar to what the brain does, and so for that reason, these little units are called neurons in parts of the literature, because the idea is that it's kind of like layers of neurons having an output or firing and sort of learning to do different parts of the task. I'm not sure how apt that analogy is, but there are people who argue it's very appropriate. I think someone else had a question, or is that? No. Okay.
Adrian, this is a pretty cool visualization. I like this. I don't want to speak for anyone necessarily, but I'm kind of trying to like think about this on the context that I go into it knowing nothing.
Sure.
And I almost wonder, like, you can see all these different colors and the weights.
Right.
But someone who doesn't really know what weights is, it might not be as kind of interesting, this visualization. And I almost wonder, like, if we introduce some sort of like simple definition of what like a very simple, like maybe like a 1-layer, 1-node network would look like with weights, if that would actually like kind of make this visualization much more powerful. If that makes any sense.
Yeah, yeah, maybe you're right. I wanted to stay away from any even minimal math today, and I promised to start adding simple but hopefully useful math next time. So we'll talk about what these simple, what they're calling neurons or simple operations tend to be. Like Bruce said, it tend to be multiplication and convolution. And that's where the weights that Andrew is talking about come into play. And then you're right, maybe with that context, this visualization will help. But I guess what I was trying to show here is that adding stacks of these operations allows you to sort of have more complex functions. But yeah, maybe it's better after, maybe it'll be more intuitive after we introduce a little bit of math. So that's kind of it for the demo. Let me stop sharing that one and reshare. Okay, so this was supposed to be only half an hour, and we're almost at the top of the hour, so I'm not sure if Andrew's going to want to do his stuff now or later, but I just wanted to mention that because sort of the idea of stacking these little operations leads to fairly powerful models, as we're going to see throughout the course. These models are just what I like to think of them as just general function approximators. So it's not really just the fact that you want to throw a neural network at every task, but as there was a question earlier about, well, I have my own model and I want to still keep parts of the model, and then just a small part of it should be machine learning. That's completely fine. It's just that part that you will approximate with this deep learning. So I like to sort of think of these as just function approximators, and they're usually in the context of complicated pipelines or complicated models, and it's just a useful tool to have to plug in different parts of it. I want to mention some properties of deep learning. in the context of these sort of stacked blocks. So because you can stack these blocks, more and more, both wide and deep, you can get to a ton of parameters very quickly. As Bruce will tell you, a lot of times, every time he asks me about something, I say, well, how many parameters do you have? And oftentimes it's like 100 million or something. And so nowadays you can get to these models being billions of parameters very easily. And so the problem with that is it gets complicated to learn them, and you tend to need a lot of data. And so we'll talk about that next time. What does a lot of data mean depending on the type of problem you're trying to solve? I mentioned that these can be thought of as complex function approximators. And all of this allows us to kind of, when necessary, do away with the manual labor that we had to do before. So for example, now if you're doing this operation of going from brain image to Alzheimer's classification, you might not need to think about how to design features, how to measure atrophy, and that sort of thing. You might still find it useful to do all that, but you might realize that you don't need to do all that, and you might just allow the model to learn all the relevant features from the images. So because we are able to just stack these operations and make the models powerful, it makes it easier for us to try these complicated pipelines in one model. And I do want to mention this is all very old theory. It's gotten a lot of excitement in the last few years, mostly because there's a convergence of things that make it work. There's hardware, so we have GPUs nowadays that are able to operate on these millions or billions of parameters and operations that we just couldn't do 10 years ago. The data is starting to be more and more available, which is really a requirement of all of this. And because all of this is converging, there's good software as well. And so the nice thing about this is there's old, long theory, so there's a lot to build on and a lot of insight already there. But it's also an exciting time because all of these things have come together. So in the next sessions, I want to talk about, choosing, I think what basically a lot of the questions were. So how do you choose the task, and how do you know if your models or the models you're thinking about are appropriate for the task? How much data do you need, and how should you think about your data in the context of the model? How do you think about the model? And here I don't mean just the architecture, but as I think, again, there was a question, how do you think about the relationships between all the entities that you care about? Maybe you have some images, maybe you have some graphs, maybe you have some output that you care about, maybe you have some diagnosis, some segmentation. How do you think about all of these, and which parts require some deep learning? And then when you get to the deep learning, how do you do the architecture, and how do you learn the parameters, which is really where we spend, I think, most of our time. Okay, so even that very, very kind of brief, vague, I think, overview, I'm hoping that helped, but even that took some time. So I think just digging deep into each of these will probably take some time. So we're at the top of the hour. I'm not sure if we want to do the Python part, but I wanted to see if there are any questions on everything, or if there are any questions or any new questions about what you would like to learn, given everything that's happened in the last hour. And whether maybe we should do some tutorials or something like that separately from giving these lessons. Any feedback, questions?
I think we should hold off on the Python because people have meetings.
Yeah.
And they're going to have to miss it.
Okay.
I guess, well, related to Python, I mean, do we want to do like kind of a non-Wednesday informal session sometime this week or next week? I guess it's up to everyone. Allison or Leah, I'm not sure if you guys have any plans for that. I do want to say that I planned the Python demo kind of like with a target audience of people who really don't know Python or general programming super well. So, it can be kind of, it doesn't have to be during live meeting, basically. So I'm happy to coordinate with everyone to see what works best.
We can potentially do it during Python school this week, which is usually Fridays at 11. I should check with Jackson, make sure there was nothing else there, and make sure other people can make it. When you, I'll write that.
That works for me.
Okay, perfect. I'll write that comment down here, and so if you can make Friday at 11, maybe you can thumbs that up, and that'll give us an indication of whether we should do it Friday or if we should save it to Wednesday.
Yeah, in Python school this week, we weren't planning to meet, so we do it every other Friday. So we're planning to meet next week. So if you wanted to take this Friday, I don't know if people are free, and that would work for them.
Okay. All right. Thanks, Jackson. All right, I'll make that comment here, and then thumbs up if you can make the Friday Python school. And wait, is there a thumbs down? No. Angry face if you can't and you want to go. I won't be insulted. Just do the angry face. Okay. But we can end the meeting and move on, and I'll just put that comment here. Thank you so much.
Thanks, Adrian. That was great. Yeah, that was cool.
Excellent. All right. So next week.
Yeah, please ask any questions on Teams or anything. Okay.
Thanks a lot.
Thanks, Adrian.
Thank you. Thanks, guys.